Module 10, Section 11.3, Geometric Sequences and Series. A geometric sequence is a sequence in which each term after the first is obtained by multiplying the preceding term by a constant non-zero real number. 1, 2, 4, 8, 16, and so on is an example of a geometric sequence with first term 1 and each subsequent term is 2 times the term preceding it. The multiplier from each term to the next is called the common ratio and is usually denoted by r. In a geometric sequence, the common ratio can be found by dividing any term by the term preceding it. Let's look at the following geometric sequence. We see that the common ratio can be found by dividing two consecutive terms, so we'll take 32 divided by 8 and we'll get 4. We could do the same with our next two terms. 128 divided by 32 is also 4. So our common ratio is 4. We get an r value of 4. So we can define our common ratio as r equals a sub n plus 1 divided by a sub n. In the geometric sequence with first term a sub 1 and common ratio r, the nth term a sub n is given by the following formula. A sub n is equal to a1 times r to the n minus 1. In this example, we want to find a5 and an for the geometric sequence that's given. Here a1 is equal to 4 and r is equal to 36 divided by negative 12 or negative 3. So in our formula we have an was equal to a1 times r to the n minus 1. So we want to find a5, which is equal to a1 times r to the 5 minus 1, or 4 times 3 to the 4th, negative 3 to the 4th. So we have 4 times 81, so we'll get a value of a5 is equal to 324. And then an is equal to our a1 value, which was 4, times 3, negative 3, raised to the n minus 1. In this example, we want to find a1 and r for the geometric sequence with third term 20 and sixth term 160. So we have that a3 is 20 and a6 is equal to 160. And remember that an is equal to a1 r to the n minus 1. So we have a3 would be equal to a1 r squared, and a6 would be equal to a1 r to the 5th. So what we'll do is we'll plug in our value for a3 and a6 into our equations, and we'll solve them for a1. So we'll get here that a1 is equal to 20 over r squared, and here we'll get that a1 is equal to 160 over r to the 5th. Since these are both definitions for a1, we can set them equal to each other, so we get 20 over r squared equals 160 over r to the 5th. So we can cross multiply and set them equal. So 20r to the 5th is equal to 160r squared. So we'll divide both sides by r squared and we'll get 20r to the 3rd equals 160, or r to the 3rd equals 8 when we divide both sides by 20. When we take the cube root of both sides, we'll get a value of r of 2. Now let's find a1. a1, we can use either definition, so I'll use our first one, was 20 over r squared. So now that we know r, we'll find that a1 is 20 over 2 squared. So it's 20 over 4, or we get a value of a1 equals 5. In this example, a population of fruit flies grows in such a way that each generation is 1.5 times the previous generation. If there were 100 insects in the first generation, how many are in the fourth generation? So we see that we have A1 is equal to 100 and R is equal to 1.5, and we're trying to find A4. So we use our definition. AN is A1R to the n minus 1. So A4 will be equal to 100 times 1.5 to the third. So we'll get a value for A4 of 337.5, or approximately 338 insects in our fourth generation. A geometric series is the sum of the terms of a geometric sequence. In the fruit fly population model, with A1 equal 100 and R equal 1.5, the total population after 4 generations is a geometric series. We see that we would add up A1 plus A2 plus A3 plus A4. So we're adding up 100 plus 100 times 1.5 plus 100 times 1.5 squared plus 100 times 1.5 to the third. When we do this out, we'll get 812.5, or approximately 813, is the total population after 4 generations. If a geometric sequence has first term A1 and common ratio R, then the sum of the first n terms is given by Sn equals A1 times 1 minus R to the n divided by 1 minus R, where R is not equal to 1. Let's look at finding the sum of the first n terms. Here we want to find the summation from I equal 1 to 6 of 2 times 3 to the I. So A1 is equal to 2 times 3 to the first, or 6. A2 is equal to 2 times 3 squared, which would be 2 times 9, or 18. So to find R, we'll divide our 2, and we'll get R is equal to 3. And we know that our Sn is defined as A1 times 1 minus R to the n over 1 minus R. So S6 is equal to A1, which is 6, times 1 minus 3 to the 6th, divided by 1 minus 3. So it's equal to 6 times 1 minus 729, divided by negative 2. Or when we work this out, we'll get 2,184. If A1, A2, A3, and so on is a geometric sequence, and the sequence of sums S1, S2, S3, and so on is a convergent sequence, and that's important, converging to a number S infinity, then S infinity is said to be the sum of the infinite geometric series given here. Given the infinite geometric sequence here, the sequence of sums is S1 is 2, S2 is 3, S3 is 3.5, and so on. On the calculator we can see a listing of our sums as we go on and get larger, and the screen shows more sums approaching a value of 4, so our geometric sequence and the sequence of our sums will converge to 4. The sum of the terms of an infinite geometric sequence with first term A1 and common ratio R, where R is between -1 and 1, is given by S infinity equals A1 over 1 minus R. So let's look at finding the sums of the terms of infinite geometric sequences. We want to find the summation from I equal 1 to infinity of 3/5 to the I. So S infinity is given as A1 over 1 minus R. So we need to find A1 and R. We know that A1 is equal to 3/5 to the first, or 3/5. A2 will be equal to 3/5 squared, which is equal to 9/25. And then R will be the division of the two, so we have 9/25 divided by 3/5, which is the same as multiplying by the reciprocal. So when we do this, 3 goes into 9 3 times, 5 will go into 25 5 times, and we'll get a value for R of 3/5. So S infinity will be equal to A1, which is 3/5, divided by 1 minus R, which is 3/5. So we have 3/5 divided by 2/5 when we do our subtraction, or multiplied by 5/2. So we'll get a value of 3/2.